Everybody recognizes this. Okay? That's the Mona Lisa. You look at, I think, apart from her forehead very carefully, and you see, of course, you can see it over here, you can see cracks. Well, why do cracks form there? Cracks form there because the paint was essentially drying up, and as a consequence, stresses were developing, and therefore cracks formed. So we're trying to work now with people in art history in trying to understand whether you can say something about what the constituents were when this was made and what you should do to prevent this from happening. Now, of course, in this painting, it's part of the allure. That's the way it's going to be forever. But you don't want to make it any worse. So you want to be able to preserve it. So how do we understand that? Well, we understand it using material science, using physics, and using mathematics. I have run out of time. I wanted to tell you about Platonic solids, but I won't, and instead I will close by telling you one thing, which is that in these examples that I showed you, in fact, mathematics is a metaphor. Okay? It's a metaphor because it allows you to abstract from an observation. Once you've abstracted from the observation, you have a mathematical model, you have some equations, which I really didn't spend any time on, but a mathematician spends a lot of time trying to analyze those equations. And what I tried to show you is that once I've analyzed them, if I was to use mathematics as a metaphor, well, what is a metaphor? A metaphor is essentially an analogy. This is not, you don't use like because it becomes a simile, but this is somehow similar to something else. And so mathematics as a metaphor is what combines and unifies many of the patterns that I show. And I'll leave you with another quote. So I'm sorry I ran over, but thank you so much.